And then I guess the first thing is that we should acknowledge that we're on Treaty 6 territory, which is the traditional meeting ground for the Cree, Saulteaux, Blackfoot, Dene, Métis, Nakota Sioux people. And we get to benefit from the fact that so much of their culture and heritage has been mitigated and repressed. And as an education institution, we are every day working hard to reduce and restore the injustice that happened to that people long ago. So we can be here because of that injustice, so we also work every day to reconcile that injustice as well. Okay, so for today, this particular slide deck, this is going to be more lecture style, but I will also say feel free to interject because I want to first say that I am a high school teacher and I know that that's a limitation. I can say things and like someone could be like, Mike, you're off your rocker. They never do that. Cool, like that's good. Like I'm totally okay with people saying that. I'm doing my best to interpret the curriculum. So I went through the entire big curriculum. I printed it out. That thing is horrible to print. Am I right? Like, my goodness, I printed it out. I taped it all together and I was like, wow, this is painful. So I printed it out. I did my best to interpret it under a computing science lens to kind of give that amount of background. I tried to relate it to some activities as much as I could, but at the same time, like I realized that that is my limitation of not being in elementary, trying to relate to elementary teachers. And to segue from that, I also want to say that the work that you all do is amazing and wonderful, and thank you so much for always being creative and thinking of different ways of teaching and engaging the students. My daughter right now is in grade 6. She's at George H. Luck. Any George H. Luckians here? Just curious? No, that's okay. But she's really enjoying her time in elementary and is very much some of the inspiration to why I want to do these sessions. I actually used her as a guinea pig for some things throughout the week, so hopefully that gives a little bit more oomph to some of the things that I'm trying to talk about. Today, where I've basically tried to break it up into grade components. I also finished this at 1 last night, so I did not have time to practice. I don't know if this will take a full 60 minutes or not. We'll kind of see how it goes. But I did want to try to bring that computing science lens into that curriculum. So with that, one of the questions that is like, well, what is computing science and computational thinking? One of the first things that I want to just point out is that your curriculum says computer science in it. There's more of a movement to call it computing science. So you'll actually see in universities, MacEwan and U of A will call it computing science. IB and AP still call it computer science. We don't know what we're talking about really. But I will say that in high school, we're also trying to call it computing science because then it relates better to computational thinking. And it moves us away from thinking that computer science is all about how do I build the next best gaming PC, okay? So when we talk about computing science and computational thinking, one of the questions that I got from the first session was like, well, what is computational thinking? And from there, what I'll say is that computational thinking is being able to think in a sequential, logical manner so that you get a desired outcome. It usually has a start and a stop, but the main idea of computational thinking is to be able to think procedurally is the biggest component of it. And to get started with that, going into kindergarten and grade 1, is that you're going to find that there's a lot that you already do. And that's kind of the thing that I want to mention with many of these courses. You already do a lot of computing science in your class, whether you call it computing science or not. We'll kind of get there, but we'll start with kind of the broad overview of what I interpreted when I was looking through that particular curriculum. And this particular slide is what's called the software development lifecycle. We go through this in high school, but one of the things that is always kind of like a paradigm shift for students that come into high school is that they think that all they're doing is programming, which in some cases a lot of it is, but there's a lot of theory that goes around the programming. So when we look at these 7 steps, the ones that are programming is 4 and 5, right? Everything else is not programming. Right? So when I looked at your curriculum, what I really saw there was that your grades kind of span all of the different aspects, and you don't really get to coding and implementation until grade 5 or 6. Now, do I necessarily agree with this? Probably not, but I do see that that's kind of where your curriculum was, where that coding only really happens in the 5-6 level. I did a similar session when the NDP curriculum was going to get released. And in theirs, coding actually started in grade 2, right? So if you are introducing coding earlier, I think that's great. I think that's totally fine. Because one of the things I had my child guinea pig over the past week was some block coding. And as a 6-year-old, she was able to use an online site called code.org, and she got pretty far into the coding process, and she was able to do basic block coding to solve problems. So I have a slide of that a little bit later, but to say that you have to wait to grade 5 or 6 isn't necessarily true. If you end up doing it earlier, I think it's totally fine. But that being said, I noticed that in your curriculum, it did say to explicitly start it in grade 5. Okay, so that leads to kinder and grade 1. So this particular section, I interpret this as like following instructions and having outcomes. And the thing that I want to say for kinders and grade 1s, and to some degree grade 2s as well, is that as the very organized and very active teachers that you are, you already have centers, you already have calendars, you have rules for your students. Like all of those following instructions that you do in class is really what this curriculum is about in that particular section. So when I looked at it, right, I started by saying it's like there's a lot of things that we don't need computers for computational thinking. And the slide that I'm going to get to is this one where I'm referencing that you already do a lot of these things, right? I would actually almost say that if there's anything that I would say to do differently would be to maybe have the fact that, following instructions is part of computational thinking. Say that somewhere, I think you're doing wonderful, right? I don't think you need to make a lot of change with it because all the things you do inside of a kindergarten classroom, whether it's centers, whether it's your morning routines, whether it's roles, all of that is wonderful. I think that's great. And that's all you really need to do, at least at the kindergarten grade 1 level. At the grade 1 level, I think the only other addition is the fact that you may want to talk about the order of operations. So I think this is kind of the only other thing in grade 1 I would recommend, which is the idea that some sets of instructions need an order and some instructions don't need an order to get the desired outcome. That's really the only other thing that I saw in there that I thought was worth noting, is that it's really all about the following instructions and procedure part of the curriculum right now is just that following instructions. Going back to this particular image of Stonehenge, the reason why I have this in here is because of the fact that when it comes to programming coding, like there is this like fear and this like, oh my goodness, what am I getting myself into? And I'll just also say, I was talking to a grade 11 science teacher yesterday, and he was like, oh, I hope coding doesn't come into the science curriculum. Just like, sorry, it's probably coming. But like that fear is just everywhere, right? And I want to really have this to alleviate some of your fear by saying that many of you, just as the fact that you're already an organized professional teacher that can manage 30 plus young children, which I know I wouldn't be able to, so kudos to all of you, but 30 young children, right, means that you already have those computational skills to be able to process outcomes that work for everyone or for most of your students. And with Stonehenge, the reason why I have this here is because this is dated to be over 10,000 years old. And it's what we actually do in our history of computing science, is we say that this is one of the first kind of algorithms that we would say existed before computers. Because although we don't know the real reason why Stonehenge exists, we do suspect it has something to do with the calendar because of the fact that the sun passes through different stones at very specific times of the year. So while we don't know exactly the indication of what those were, and the fact that also our Earth rotates, axis changes a little bit, we can surmise that it had something to do with the cyclical nature of the year, and that's what they use it for, a giant calendar, is what we think. right? And that kind of idea where we don't need computers to think computationally is kind of the thing that I think they're trying to foster in the early years. So with that, that's kind of like kindergarten and grade 1. I think that like being thoughtful that you're already doing everything you need to do for it and you're doing a great job with it. It is really just like throwing in, hey, instructions lead to an outcome, which instructions lead to the desired outcome, which ones don't. It's good enough. I also talked to my grade 1 English teacher right now, and she also mentioned that at the kindergarten grade 1 level, they're not really explicitly making it a unit. So I also kind of think that's pretty okay at that level as well. Okay, grade 2s, completely different story. Does anyone here teach grade 2s? Okay, a couple of you. Did you not notice that like your like section was like this much longer than everyone else's section? It was like, why? So when I looked at the grade 2 section, there's a couple things that I want to point out first about the grade 2 section, is that the grade 2 section doesn't use this term, but it uses this term. And I say this because there's a section that's like, a series of instructions all have verbs, and they have a start and an end time. So they had a handful of bullets. And the reason why I think it's important to introduce this term in grade 2 is because one of those sections, I should have probably screenshot it, but it does have all 4 sections of an algorithm, which is like a more layman's definition of an algorithm is that it's an easy to follow actions performing a task in a given time, kind of like a recipe, right? So if that is the definition of an algorithm, that is like more like less technical, then when we look at the different parts of the algorithm, readable instructions, so like I said, you have a section that's like instructions need to have verbs. They have to have a start and an end time. They have to have an outcome of some sort. This is literally the definition of an algorithm. I don't know why they waited to grade 4 to throw the word in. Okay. So when we talk about an algorithm, what I would say about an algorithm is that, once again, something very much already built into the things that you do every single day. When you have things like, you're teaching about scientific inquiry. There's a box there. Teaching scientific inquiry, and you have step-by-step instructions, right? When we talk about, okay, like getting ready to go to the park, getting ready to go outside, there's a series of instructions that you do. There is the screenshot of the poster of a morning routine, right? What many of you do with your students with having a morning routine. This would be something like an algorithm. So just a series of instructions that actually get you to an outcome. A lot of examples that I see online tends to be getting ready in the morning is one that a lot talk about. So what are the series of steps that you have to take to get ready in the morning is a good conversational activity to do that also links to the identity unit. And then from there, being able to identify, well, like what is the outcome? Well, the outcome is to get to school, and what is is there a start and a stop position? So we have our outcome, right? The outcome is to get ready to learn, right? And we have a start and a stop position to it. So this would be an example of an algorithm with the series of steps that they're taking in order to get to a particular outcome. So once again, not necessarily anything about coding. Really, it's just about understanding instructions and following instructions. At this particular time, this is where I would also say that there's a creativity component in your section as well. And the creativity component, one of the things that I pointed out in here is that what I will do with my students for an example of creativity is that they have a place for a robot in a maze, and like what are some of the different solutions to do that, right? Like you can follow it exactly the steps. You could, someone might say it's like, well, if your hand's always on the right wall, eventually you'll get out. Like having them to have the multiple different solutions. I really wanted to read all of the curriculum. I honestly just didn't have time. I literally only read through the science ones. But I remember in like math a while ago, there was like showing different ways that you can solve a problem. Something like that could be a way of relating this to the math curriculum. And I would say that just because like the NDP one had it in math, so they had more math examples of this. But having like 3 + 4 = 7, 4 + 3 = 7, different solutions like that could be a possibility. I have a comment.
If you have the time in your classroom and the budget, right about this age, you can start
Cool.
And it starts off super simple, and then the challenges get much more difficult.
Okay, I love it. I love it.
You've got 10 copies in the room, you can
No, that's great. What we actually do with our high school students, very similarly, is we will get them to either try to do instructions to put on a jacket, right? So they work in small groups, right? Write down instructions, put on a jacket, and then me being the teacher will attempt to do it as ridiculously as possible by only following exactly what they say. The other one that we've done also before that is the following instructions and multiple ways is making a paper airplane. That one gets a little hectic sometimes, but that's one that when they're like creatively like, well, if I tried to make different airplanes, that would be one as well. I think I even might use that later on in here. I don't quite remember. The other thing I'll say for creativity is that it's also like building upon this example is that it's like, okay, well, not everybody takes a bus, right? What are some additional options like being able to have that conversation? But I would still say here at the 2 level, it really is more about the concepts than it necessarily is about the programming. And the concept that the entire section is dancing around without actually saying is like the fact that you're trying to teach them the definition of an algorithm. Okay. The other one, if you want to use something a little bit more sciencey related with programming, is sorting algorithms. It's actually one that we do use as well. So there is a couple types of sorts that we use. And oftentimes, I'll do it with playing cards on the screen, but I also know teachers that will use like just like numbers and then get their students to be up on at the front. So 5 like volunteers, and then what we'll do is that we would end up sorting them with different sorts, and then they can see some of the different ways that they could do it. These here are probably some of the simplest ones that I would recommend. I don't know, do we have time? We probably have time to do I have 5 volunteers? We can try this. Okay, if you want to just come on up, come on up. Okay, this does work when we have 5. All right, so let me give some numbers. Okay, we'll get you all in a line here at the front. Okay, you can get a number. You can get a number. And then do we have another person coming? You can get a number, and we'll get one right over here. Okay, so what we do for something like bubble sort, we have 2 partners always comparing numbers together. So I'm going to first get you to take 1 step to your right. So only the one, only the one, only the one. Everyone's excited. Okay. So then how bubble sort would work is that we would have the person on the rightmost of this group take 1 step over, and then they compare their numbers and say, which one is bigger? Bigger one is, then they'll swap positions, so that the bigger one's on the left side. Yep, very good. Okay, and then from here, then we'll have our another person take 1 step to the right, and then you 2 will also choose, and then we'll have the next person, and then same thing, you 2 compare, and then you 2, and then compare, and then we can ask which one is the one that is in its right spot. The 4, very good. Person at the back, very good. So then we have our 4 that's ready. So number 4, if you can take 1 step to your left, because you are now sorted, right? And then we're going to get, from here, normally I have more space. So I'm going to get a little more space. Yep, you 2. So do they need to move? Nope. Okay, so then they're done. So then, and then now that you're at the end, so you take your step over. You're also now part of the sorted one. And we move over, and we do it again, and then normally the kids figure it out. Right? And then we're done. This is a good point to actually mention, it's like, while the sort is done, is the algorithm done? Are we done all our steps? Right? Right? The goal was to get smallest to largest, which is what we are. Right? Sorry, I probably missed that part, but smallest to largest. But this is something I'll say is like, well, is the algorithm fully done? We finished placing number 2? Did we finish actually placing 1 and 0? Right? So then being able to talk about how the algorithm isn't actually quite done, even though the sort is. And this is actually something that I'll say, we're going to do one more example, because we want to do it a second time with a different method. But this is where I'll also say, this is where I start telling my students, their brains are faster than computers. Right? Your brains are faster than computers, because you can see that this is fully done, even though we're not done the sort. But the computer isn't going to know. It's going to keep looking at 2, 1, and 0, even though we know it's done. Okay? So that's something to be thoughtful, that our brains are much faster than computers when we look for patterns. Okay. I'm going to get the 5 of you to choose to mix up, and we'll do one additional method of sorting. Okay. Okay, so now we have our arrow, our fun arrow. So then this selection sort, how this particular sort works, we're still sorting from smallest to largest. Our goal is to find the smallest number, put in the smallest area. So then what this particular sort does is it first assumes person 1 is the smallest value. So I'm going to put my pointer here. I'm actually going to get you to hold the pointer. And then normally I get another student, but it was like pulling teeth to get these 5 people up, so I'm not going to try to get another person. So then I get the other student to be like, to then look, it's like, okay, is this number smaller than the pointer? No. Is this number smaller than the pointer? Yes. So then we're going to take the pointer, put it here. Is this small number smaller than the pointer? It is, so we're going to move it. And then is this number smaller than the pointer? So now that we've done finding our spot, we are then going to switch the person with the pointer with the person all the way at the front. So number 3, you're going to come here. Number 0, you're going to take a step to your right. You are now sorted. So now, starting here, no, thank you. Pointer here, right? And then we ask, is this number smaller than the pointer? It is, so the pointer moves. Is this number smaller than the pointer? It isn't. Is this number smaller? It isn't. So now we got to the end. So our pointer switches with the lowest part of our unsorted section. So our 4 and our 1 will switch. Our 1 will take a step to the right and give the pointer back to 4. We now do the same thing. So we see this, and then hopefully the students will start wanting to go faster. So do we need to move the pointer? Yep. And then do we need to move the pointer? And then once again, we'll do the switch. And then the 4, you got to switch with her. So you would have been here, right? So this is, again, when we see, and the pointer should be right here, right? Yep. But here's where, again, we see it's like, okay, we're technically sorted, but there is a sorted section, and we still need to finish. So then this is where kids will be like, oh, like, you know, are we done? Or it's like, well, no, technically, there's still a little bit left. Whether we choose to finish it or not is up to us. I think sure, we'll finish it. So then we have our pointer here. So then we ask, is this number bigger than this one? It isn't. So then our pointer is where our smallest value is. So you just take a step to the right, give the pointer here. Our pointer can only look at itself, so then it knows it's the smallest. So it takes a step over, and then finally now we're all sorted. Okay, so that is how it works. Thank you so much, and then we can get all of the pages back.
Thank you.
Right. No, it's fine. Thank you. Right. So what I do with my students, even in grade 12, is I will have a bunch of decks of cards and be like, figure out some sorts, right? And then get them to explain some of the ones that they've come up with before we have to go through the ones that we're supposed to for our curriculum. So that is a way of doing it creatively with different outcomes and different strategies, but also with that computing science lens. Okay, where's my pointer? Oh, the other thing that I'll also mention is that there's a lot of different sorting algorithms. Some are ridiculously complex. I would just stick with these 2, or maybe insertion sort would be another simple one to do. I wouldn't try anything more ridiculous than bubble selection or insertion sort. Okay, we're still in grade 2. Grade 2 is a big one. It is the way it is. Grade 2 also has a debugging section. So what I'd say for this one is also just putting it in the conversation or built-in activity where you're talking about the algorithm steps, that if you are not getting the desired outcome, what changes could you make to get that desired outcome, right? Today I had to be here at 8:15. We got up a half an hour early, right, to be here, right? So what was the change in an algorithm in order to fix something so that if something is going wrong, we fix it? This is something that I would say also works a lot well with math when we talk about procedural like borrowing and carrying numbers. Do we teach borrowing and carrying in elementary, or is it something different now? Okay, borrowing and carrying, right? Being able to say it's like, well, if I'm not getting the right answer, where in my steps of borrowing am I doing something wrong, right? So then being able to deconstruct those steps is kind of the other thing. Grade 2, I feel like, has a lot in it, but most of it is just like ideas. Okay, the other idea in grade 2, I'm so sorry, grade 2. Grade 2, you got a lot. So grade 2 also has the idea of repetition. So for repetition, these are, once again, things that you can incorporate into this discussion of these scenarios. When we were doing the example here, like another thing that you could say as the students are doing this sorting activity is like, where did you find that you're doing a lot of repeating, right? How does the algorithm repeat? That would be good enough questions. This is a little bit more technical than what you would need to be able to explicitly teach, but just to give you an idea that there's two different types of looping. There is for looping, which is saying like for like every Monday, Tuesday, Wednesday, Thursday, Friday. So giving specific how many times it repeats. So this could be it repeats 5 times, right? This could be for each button, right, on a lab coat. Then you have to do the action of threading the button through the buttonhole, right? There is, and then finally you have an actual chef. There could be for a time, right? So for 60 seconds, you're supposed to be washing your hands. Not that my 6-year-old does that. So a time component or a number of steps component, a counting component, is what we'd say for like a for loop. Then there's something called a while loop, where until a condition is met, you keep doing that. So while I'm not at the door, take a step towards the door, right? So having that condition be once you get to something or once you get to a particular outcome, then you stop, okay? So the while one is more of like when you reach an outcome, then you stop. Okay. For is you count. So those are kind of the two different ways. Okay. So this is an example of while loops for like a math example, because once again, when I did this before, there's a little bit more math examples, but starting at the rightmost column, while there's a digit on the left, right, then you would still keep adding, right, would be an example in class. Okay. Okay. Oh, look, I actually have things moving. Okay. I thought I removed all of the moving things, but apparently I didn't. Okay. So add bottom digit to top digit and then move one to the left, and then you keep doing that until you don't have any more columns. Okay, this is also another one that was like if you want something that's just like kind of a while loop for something more conceptual, right? So that is just another example. This one was like, this was like at the height of COVID. There's a little slide in here, being resilient. But hopefully this just gives you some ideas on how you can word things. And once again, at the Div 1 level, a lot of this stuff isn't like I need to do this as a unit, right? It is something that you can just incorporate to a lot of other things that are already pre-existing, which I thought was like a good, gentle way to get into teachers and students to get into coding. I will also say that because at the 2 level is where the grade 2 level, like is where places like, what is it? No, the word. It is like that after school program that does coding. It's not Class Dojo because that's an app. Code Ninjas, thank you so much. Code Ninjas, right? Code Ninjas really starts to get into block coding heavily in grade 2, the 7 range, because they start at 5. that like you may actually get students starting with more coding at this point anyways, if they're doing some more of that extracurricular. But the fact that it's not in our programming, to what extent you have to introduce at that age is really up to you. There is some resources I'll still give about, like if you want to start coding earlier, grade 2 I think is a pretty good place to start. This is some of the extensions. So this is something that if you are part of Edmonton Public Schools, like the Technology Implementation and Planning Supports team, the TIPS team, used to also advertise, I think Career Pathways is now the department that will have tools like this. So you can always get connected to the Careers Pathway consultant. And they do have kits where they have things like a Codapillar. I don't know if they have the Codapillar anymore, but these are tools where, as you can see with this particular caterpillar, that there's a set of instructions for it to move. And one of the activities is that you have like a start location and an end location, and like the kids have to try to get the caterpillar to go from the start to the end. If you have a handful of these, doing it in a gym with your kids in groups will be quite engaging for them.
So to go through the ETA library.
The ETA library also has them. Great. Yeah, so this is one that I'd say is like a good starting point because it's very intuitive for your students to understand that step-by-step instructions and coming out with an outcome. As I mentioned before, I guinea pigged my child for code.org, so that's this particular one. So the logo doesn't do the name of it justice, but it is code.org. And I just mentioned in my previous session that with code.org, they have sections for K to 12, or sorry, K to 6, K to 12, K to 6. And in there, they also cut it in half where there's a section that is pre-reading and a section for reading. So you could get students that do lessons that start from the very beginning of like click and drag a block all the way to activities where they're trying to put pieces together. So this is one of their like pre-learning ones where it's pre-reading and they're just learning how to put blocks together. So it works great on a Chromebook or on iPads. And that's one that if you are interested in incorporating a little bit more like actual programming into the grade 2 area or use it as part of the teaching, code.org is a great one to start off with. I do just want to mention for Edmonton Public, it is a pre-approved third-party application. You don't need to create an account in order to use it, but if you do choose to use it long-term, you can. You just need to do parent notification before your students create an account. For the other divisions here, you would need to check with your own district information on what is needed and whether or not you can use it. But my 6-year-old she tested this on Saturday, and it kept her occupied for 40 minutes. So it was pretty good for her. So just to give you an idea that like some of the students will take it and they'll do really well with those extensions. Okay, that was a lot for grade 2. Grade 3. Okay, sorry grade 2, yours was just really long. Okay, computational thinking and creativity. So in grade 3, they're talking more about deconstruction of an algorithm into steps. So these two concepts were kind of the main things that I pulled from it, where it's deconstruction and it's pattern formation. So being able to take a series of steps and then parse through all of the steps individually, but also be able to find patterns of the steps that are inside. And the reason why this is important in the grade 3 level and how it can link to the grade 2 level is because when you can identify the pattern of cutting and washing for the different materials inside of creating a sandwich, then when you talk about the algorithm, then you can incorporate things like, okay, well, where can we find repetition? Well, we can find repetition by when we're getting our sandwich ready, we have to cut the bread and the cheese, right? So then part of our algorithm of making the sandwich, we can say like cut and then repeat for these two things, right? So that is kind of where I saw the link more, was that they have to be able to take a series of steps, deconstruct it. When we talk about it in high school, we talk about being able to explain things step by step. So that kind of mentality of like, well, why do we have to go through all of these steps? And then is there a better way that we can do it? And that's kind of where the pattern formation is. So once again, it isn't necessarily a lot of its own unit, I would probably mix this in with one of your other science units where you're dealing with scientific inquiry. When you're dealing with living things is probably a good one where you can mix this one in because certain plants grow in certain ways, right? That kind of pattern formation and deconstructing, well, what does a plant actually need to live, right? Those kinds of things can really be found in some of your other units. So once again, not something you explicitly have to do. If you were going to do this, then I would say that the thing to do more with the block coding is to focus more on how to make code more efficient so that you're using repetition more if you are using block coding at this particular level. Anyway. Okay, what is our time? Okay, we got 20 minutes. We haven't even hit div 2. How are we feeling? Do we have any questions? Are things going okay? Okay, hopefully the things I'm saying are kind of useful. We'll see in the feedback, I guess. So the other part of creativity, I forgot this slide, sorry, is that the other part of creativity with deconstruction is that if something is different, so in this example, like if you ran out of bread, right, what could be a solution to how can you change this particular algorithm to still get a similar outcome? So it's like, oh, if we don't have bread, make lettuce wraps, right? So that could be another way of incorporating that creativity from that deconstruction pattern formation. And then I think the other one was divergent thinking. That's kind of where you can do this, like if we are removing some items, what else can we create? I really tried hard to do my homework and read all the curriculum. I hope it shows. Problem solving and inquiry. Okay, this is a good point for me to actually go with this quotation. When we really talk about computer science, it's not about how well you know how a computer works, right? It's how well we use it. And that's kind of the idea of now we're really talking about the realm of algorithms, right? So I mentioned in grade 2, it does kind of make sense to introduce it there. But in this particular section, right, this is where we can talk about what are the main components of an algorithm when we are joining other algorithms together to make a program. So that's kind of where, before we're just talking about algorithms, how does that transition to a program? Well, a program is a bunch of algorithms put together, and here's some of the ways that we can put them together, right? We either put them together sequentially, which is step by step. So one algorithm leads to another algorithm, which leads to another algorithm. Getting dressed in the morning algorithm leads to, getting dressed in the morning algorithm leads to going to getting on the transporting to school algorithm, then leads to the learning in school algorithm, then leads to the going home algorithm, and so on and so forth. So stringing them together would be sequential. Also in the idea of stringing them together, what algorithms can repeat, I think is a good part in this idea of making a bigger program. And the last one is in grade 6, which is selective. This is the conditional statements of if-else. So while you don't really get there into grade 4, the thing that you could talk more about grade 4 is just that a program is a composition of algorithms that make bigger and more complex outcomes, right? Because up until this point, it's just like do one thing. Now it's do one more complex thing with multiple algorithms leading there, okay? The example that I gave in the previous session, sorry for the repetition, is the idea of creating Thanksgiving dinner, right? You have multiple algorithms on the go, right, in order to make Thanksgiving dinner, right? And the same thing with making a program, you will have multiple algorithms that are strung together sequentially that will then make your outcome, okay? Okay, and of course, I had to have an example with food. So this example, if you look at it more closely later, I'm not going to go through it now, but if you go through it in your slide deck, it is written more like a programming set of instructions than a baking instructions, but the desire so that you can kind of see the similarities between the two, okay? Okay, so in 4 also, it does have a build and construct section. And this is where I would say in the build and construct section that when we talk about the complex program, I would incorporate it into one of your other science ones where they're building something and they're testing it, if it works or not, right? So these are two pretty like low-hanging fruit examples, although I question like an egg breaking challenge in elementary. But I would say like if they are able to build something and test it, I think the other one that I saw was a good suggestion was like making a tinfoil boat with the coins, right? Would be another one of, okay, how can we, like what are the algorithms that I need to build something to construct it? And then the fun part of testing it, which normally means breaking it. The other solve a problem one that was thoughtful is if you're in the gym, there's like the activity was like, newspapers or magazines. I know those don't really exist anymore, but making like the tallest tower in groups, those types of STEM building activities. Tallest tower, the straw bridge, but paper bridges, and then testing them with books, right? Those are types of things where you can do where they're more cross-curricular. But once again, if you are doing it in programming land, then in programming land, many in code.org, you get to a point where the students, I don't have the picture on this set of slides, I have it on a different one, where the students will start trying to finish challenges. So very much like what our gentleman mentioned with trying to get a robot to a location, code.org and also Scratch both have lessons where you're trying to get a robot or a bird or a squirrel to get something on this like grid. And from there, then in that grid, then that's also solving a problem, but with computers and programming and block code. I don't have an image of that here right now because I didn't anticipate talking about it, but it's a good one to bring up. That's what I would probably do if I was doing more code-based, is what are the sequences needed to get something to somewhere on a grid. Maybe I can find an image later. I'm just looking at my time and being like, I clearly talked too long. Build something. These are just the other one that if you don't want to solve a problem by constructing something, you can also build a model, right? So whether it's a terrarium, whether it's the constellations in your stars unit, right, that would also fall very well into this particular idea of building something complex from smaller algorithms. So the constellation one, I think, would be a good one to do kind of as a class, because then you can first have each of the students do their own algorithm to make their own constellation. Then as the class kind of map it all out, like together and being like, okay, all of us did our own algorithm to make the one big program, which is the night sky of our class. So that would be something I could suggest for that. Out of like, was a terrarium, like do you guys do terrariums in elementary, or is that also too complex? I hear more no's than yeses for the few that are participating. Okay, good to know. I'm trying my best to understand what makes sense and what doesn't. Okay, that leads us to grade 5. Create computational artifacts. So this is where you're most likely going to get into block coding because of the fact that in the curriculum, I know it said that there's a bunch of artifacts like creating an image, creating an animation. In my previous session, my recommendation is actually to create an animation with block code, but this is where it has very explicit things like use visual block codes to do things, and that computers follow code and a programming language. So this is where, if you've been avoiding it, you will probably have to incorporate some block code of some sort. This is an example of an animation that your students can do. This one is probably much more complicated than what they can do in a single session, but being able to use, this is using Scratch, and being able to control Scratch the cat, and then getting him to do something, maybe doing some kind of lesson like this where there's a story part of it. That's something that your students can do at this level where they don't need to actually use conditional statements to make something like this happen. There's a lot of tutorials. I wish I could say it's like, go to my session, but my session happened this morning before where they did a simple animation and used block code to do that. So what block code looks like is this, where you can kind of think of it as like linking cubes or puzzles, where every piece has a particular action, and then that action is going to control something that happens on that screen. So this is, if you've never seen block coding, this is generally the standard of what block coding looks like. Scratch isn't necessarily the program that invented it, but it's the one that is the most well known. And I really, this is the kind of the other thing is that you'll notice that I don't want to lead you to like obscure places, because then you don't get a lot of good tutorials online. If you Google Scratch 3.0 like lessons, you will find a plethora of lessons at multiple different age groups. Also, their website has an educator section, which they give their own tutorials as well. So it's very well built to introduce students to Scratch. I will also say a bunch of your students will already know Scratch by this point because they've learned it elsewhere, like at Code Ninjas. Question or comment?
Do you think, a question more or less, do you think using the CS Fest platform would be more suitable to introduce elementary kids to Scratch?
The CS.
The CS Fest, the one that Google has.
Okay, so the one that Google has, I will say that it's newer, so you have less resources with it. I would say that most people in elementary implementing coding, I almost always will hear about Scratch. So it's one of those things where like if you're trying something different, you just may not get as much support. But I'm also seeing some hands up that they may want to counter what I just said. So we'll start there and then we'll go there.
I was gonna say, the only thing is Scratch Junior is easier than this. And the kids know it, like, as soon as they start playing with it, they'll know it better than you.
Okay, and then
The other thing about Scratch is it's accessible on Chromebooks, super easy to use there. Kids don't have to make an account to save their work, so you don't have to send out permission slips to parents. They automatically get saved to your Google Drive. Sharing it is a little bit more of a pain, but it's way easier on your side.
I will also say, just to add on, that if you are Edmonton Public Schools, they've already approved of Scratch as well, you would just need to send the parent notification. You don't need a permission form, you just need notification. So, yeah.
We need notification to use it because we're not sending any personal
No,
information.
you only need notification if they are going to create an account, not if they're just using it.
And you
Yeah.
can save everything on Scratch
Yeah.
without creating an account, which I hate sending stuff home and stuff. So
For sure,
there's that too.
for sure. Yep. No way. Does that answer your question?
Yeah.
Okay, awesome. Okay, and thank you so much for your responses, because once again, elementary teachers, you know your stuff better than I do when it comes to some of the elementary level things. Okay, grade 6, abstraction. How much time do we have? We got 10 minutes. Okay, let's get this done. Abstraction and developing artifacts with decisions. So this is where there's two components. There's the abstraction component, and there is the developing artifacts with decisions, so if and else statements. So the abstraction part is the part that I'm going to go through first. So, oh no, what in the world is abstraction? It is the process of deconstructing a idea, entity, a something into its most basic form needed to perform a task. So an example of this that I use at the high school level is that when we're doing calculations for high school averages for things like the Rutherford Scholarship or for university admission or for in-school awards, right? I tell my students, it's like, well, you know, all of you, like some of you are great personality, some of you have, you know, are taller than others, some of you have different hobbies. While that is part of the characterization of that person, none of that's important to me calculating your average, right? The only thing that I need for your average is what courses you're taking, what marks you got in them, and your student ID, right? That's it, right? So that idea of only using the properties and the actions needed to perform a task is the idea of abstraction. Another way that you can think about it is that you can also say, it's like, well, you know, when you're playing a video game, right, how do you make Mario jump, right? Well, you do that by hitting a button. You're not actively jumping to make Mario jump. So then the abstraction is the idea that you have to push a button to make something happen, is the abstraction of the action of pushing a button, not actually jumping, right? So those are just kind of like broad examples of it. To give a more guided example is that when we talk about abstraction, we normally talk about in the realm of what's called an object, which is just basically anything. And an object is composed of two things, properties and actions, right? So then you can talk about, it's like, okay, well, when we talk about abstraction, well, what properties do these dogs have? Well, these properties is that we can look at one, and it has a particular color, it has a particular fur texture, right? It has a particular shape of its ears, right? So that would be something that is for this particular dog, right? And then we compare it to this dog, which has the same properties, but different values. So how we differentiate is that they have different values for those properties. Right? So that is the idea of abstraction, is that we are breaking them down to just what we need to do the task, and it is the values of those properties that differentiate. From there, there can also be differentiation in the activity, in the actions. So like I have like a cry, which like this fluffy dog barks, right? They both eat and sleep. They may have different values on how much they need to eat and sleep, right? And then for the actions, like this dog more does a howl than a bark, right? And then like it also eats and sleeps and has its own values, right? So the idea of abstraction is really what are the properties that we need to perform the task, and what are the actions that particular thing has to do to perform the task. Those are kind of the ways to separate what it means by the idea of abstraction when it comes to what I read in your curriculum, kind of what we do in programming. Okay. So hopefully that can give you some ideas of what abstraction is. Okay, then this particular slide, like you can have multiple objects that come from the same template. This is where one of the questions that you can ask is like, well, okay, like what makes a table, right? And then like the students will list like what are the properties, what are the actions, right? And then you ask, well, is a stool a table? And then you go through, it's like, okay, well, what are their properties? What are the actions? And you'll always get the kid who's like, well, you could sit on a table, Mr. Zhang. And I'm like, yes, you can, but it doesn't make it a stool, right? So having that particular activity is like, well, what makes one thing different from another? What is that property, or what is that action? Because really, the only thing that's different from a table and a stool is what the main action is supposed to be, right, than anything else. So that is the idea of abstraction. And then, oh yeah, I put our little guinea pig here, our gerbil guinea pig, it's a something. To say is like that, it may have similar properties, but then what makes it different from the other one? So similar to the table and stool example, what makes this particular object different from other ones from those classifications? Okay, and then you also have generalizing patterns. So generalizing patterns, okay, well, we can now generalize that, well, while we've separated the gerbil from the dog, they do have similar properties and actions, right? So then we can put them under a bigger classification, right? Okay. This is also an activity that you can try. I've done this with junior high kids, so I don't know how well it'll work with grade 6s, but the idea of this, and like there's also a board game, which is just really glorified Lego called Creationary, where the aim of it is that you're given something and you're supposed to try to build it in Lego. So one of the things that I did with junior high students is like, what is the least number of blocks you need to build something in which someone else can figure out what you built? Right? Because then that also plays into the idea of abstraction, where it's like, what is the least amount of properties it needs to show in order for someone else to figure out what it is, right? So that would be something that you could do with an activity for abstraction. Okay, decisions, our very last one. I also see some of you are like, Mr. Zhang, stop. So okay, we're going to quickly finish. Okay, if-else statements. If something happens, we do one thing, else we do another thing. If it is raining, then we go out and bring an umbrella. If it's not raining, then we can go outside and play. Okay? So if statement, else statement, right, is the idea of decisions. You can consider them as true, false, would be another way of describing them. They can also be more complex, right? If it's raining and it's also windy, bring a jacket, else you can bring an umbrella. Or if it's snowing, well, just bundle up, right? Else you can just wear sunglasses, right? Because the only thing left is being sunny. So it can be more complex. These are called nested conditional statements because there's a conditional statement in a conditional statement. And whether you call these decisions, selections, conditional statements, they're all just these if-else statements. Okay. Okay, algorithms in math. So we have borrowing, right? So if we have to borrow, so if the top digit is smaller than the bottom digit, then do all of the borrowing steps to then be able to borrow, right? If it's not this, then you don't have to do this at all, and you just keep going, right? So separating if and else, right? So this helps with the computational thinking of like procedurally, like when the procedure branches off and there can be two or multiple outcomes, right? So going back to the idea of outcomes, two or multiple outcomes. Okay. This is where you can make much more complicated things in programming because of the fact that you can use if-else statements. This is where you can do things like inputs. So if the W key is pressed on the keyboard, the sprite moves up, right? If the sprite is clicked, then it does something, right? So that's where you can have more interaction. So in grade 5, I mentioned animations. Grade 6 is like games because they can interact in those games. And it's more than just setting a series of instructions. They have to also worry about inputs. So what are they pressing on the keyboard? What are they clicking? Are the things that you are going to be thoughtful of, okay? This one I also had my previous one, but you know, where, you know, we're really here to, you know, just keep trying, right? And the fact that you're here, whether you tried it this year or you're trying it next year, right? We're all in this together, and it's totally fine to take steps to figure it out. Resources. There are some great coding books. This is one I found at Costco a few years ago. I don't know if you can still find it, but it's one where you actually use flaps to actually do the coding. So it's all in the book itself. And then you can generally find things like this. Many of the like really elementary coding books, I wouldn't necessarily.
Was for some reason was like had to.
I wouldn't necessarily. Okay, let me start that sentence again. Some of the really basic ones, like the pre-kindergarten ones, I think are a little too simple. But getting ones where there's like moving flaps are really good. Other explorations, we already mentioned code.org as a great one. Warrior.js, oh, this image didn't load. Warrior.js is really for your extreme high achievers. This one is all text-based, but they will write their text. They're kind of finishing quests, very much like the board game or what they would do in code.org. So this is an idea of them performing a task where they have to use direction blocks to get the bird to the pig. So that is building or achieving something through code. That was a grade 4 example. And then this one, I would only say Warrior.js. Grade 6s, they already know how to code. They just need something more, right? This one, it's all in JavaScript. Warrior.js also doesn't give them all of the instructions on how to use JavaScript, but it gives them the environment. So they would have to go to someplace like W3 Schools to learn JavaScript and play along, okay? So that one I would say is like really like only for your really high flyers. And then code.org, if they want to get started earlier, like I said, grade 1, grade 2, you could get them started on this. Or if they just want another environment, they can skip to higher ones in code.org if you want to give enrichment at the 5-6 level. But I do find at the 5-6 level, I imagine that Scratch, they just get to do a lot of different things in Scratch. So they'll probably be fine with just that. Scratch also has a bunch of lessons. We already kind of talked about that. I'm kind of just going along because we should be done. Shameless plug, I wrote a technical manual about Google Classroom. So in case you want some support on learning how to use Google Classroom, there's a chapter about online teaching. It is there. Shameless plug, shameless plug. Credits for where I got the particular slide deck. And thank you so much for being here. I don't have anywhere else I need to be after, so if you have specific questions, feel free to come up and enjoy the rest of GETCA. Sorry, this took 3 minutes longer than it should have.